Welcome to my channel. In today's video, we will be discussing how quantum computers can be able to break encryptions. Many people are concerned that some codes used to deliver secure messages will be vulnerable to cracking by quantum computers. The question codes encrypt data using trapdoor mathematical functions, which are simple to use in one direction but difficult to use in the opposite. This makes encrypting data simple but decrypting it challenging without the aid of a unique key. These encryption methods have never been completely impenetrable. Instead, their security is dependent on the enormous length of time a traditional computer would need to do the task. Modern encryption techniques are made to be so difficult to decode that they are almost impregnable. Quantum computers, however, alter this perspective. These devices ought to be able to crack these encryption with ease because they are much more powerful than traditional computers. When will quantum computers be potent enough to perform this, then, is a crucial point that is raised. Any data that was encrypted using this method prior to that date is no longer secure. So, in an effort to estimate how much time will pass until such a machine can be developed, computer scientists have tried to quantify the resources such a quantum computer might need. Furthermore, decades have always been the response. Thanks to the work of Martin Ecker at the KTH Royal Institute of Technology in Stockholm, Sweden, and Craig Gidney at Google in Santa Barbara, that way of thinking needs to be altered today. These researchers have discovered a method for quantum computers to crack codes more effectively, requiring orders of magnitude less power. Because of this, these devices are much closer to reality than anyone anticipated. For governments, military and security agencies, banks, and anybody else who has to secure data for at least 25 years, the outcome will be unsettling to read. First, some context. American mathematician Peter Shor created a quantum algorithm that performs better than its classical counterpart back in 1994. The key to deciphering trapdoor-based codes is Shor's algorithm, which factors enormous numbers. Trapdoor functions are based on the multiplication operation, which is simple to perform in one way but much more difficult in the opposite direction. For instance, adding two numbers together is simple. 491,597 is equal to 593x 829. Finding the two prime numbers that must be multiplied to arrive to the number 491,597, however, is difficult, and as the numbers increase, it gets harder and harder. In fact, the most widely used type of RSA encryption, which is based on the notion that 2048 bits is nearly impossible for a classical computer to factor, is based on the assumption that this is practically impossible. Shor demonstrated that a sufficiently potent quantum computer could easily accomplish this, which had a startling effect on the security sector. Quantum computers have been getting stronger ever since. A 4-qubit quantum computer was utilized in 2012 by researchers to factor 143. Then, in 2014, they factored 56,153 using a device akin to that. It's simple to think that quantum computers will soon be able to outperform the greatest classical ones if development continues at this rate. Not so. Contrary to what would be anticipated, quantum factoring actually proves to be much more difficult in practice. The cause is that noise is a serious challenge for massive quantum computers, and currently, using error-correcting codes, which itself necessitate a considerable number of additional qubits, is the best approach to deal with noise. Factoring 2048-bit values becomes significantly more resource-intensive when this is taken into account. In order for a quantum computer to function consistently, experts predicted that it would require 1 billion qubits in 2015. That's a lot more than the 70 qubits in the most advanced quantum computers available right now. On that basis, security experts would have been able to defend the notion that it would take decades for a quantum computer to decrypt messages using 2048-bit RSA encryption. Gidney and Ecker have now demonstrated how a quantum computer might perform the computation using only 20 million qubits. In fact, they demonstrate that such a machine could do the calculation in just 8 hours. The worst-case estimate of the number of qubits required to factor 2048-bit RSA integers has decreased by roughly 2 orders of magnitude, the authors claim. Their approach focuses on an improved way to carry out the mathematical operation known as modular exponentiation. Finding the remaining after raising a number to a specific power and dividing it by another number is done in this manner. The operation in Shor's algorithm that requires the most computing is this one. However, Gidney and Ecker have discovered a number of techniques to optimize it, greatly lowering the amount of resources required to perform the algorithm. This is a fascinating piece of research that should have significant ramifications for anyone storing data going forward. Today, the idea of a 20 million qubit quantum computer looks like a pipe dream, but the real issue these experts ought to be asking is if such a gadget is really conceivable in the 25 years they want to keep the data safe. If they believe it to be, they will require a new type of encryption. Security specialists have created post-quantum codes that are impenetrable to even a quantum computer. Therefore, it is already conceivable to protect data from attack by quantum computers in the future. But these codes aren't yet accepted as industry norms. There isn't much risk for regular individuals. For operations like sending credit card information over the internet, the majority of users utilize 2048-bit encryption or something comparable. Little will be lost if these deals are recorded today and broken in 25 years. For governments, though, the stakes are higher. In 20 years, the messages they convey now between embassies or the military, for instance, might be crucial and merit maintaining a secret. These firms need to start worrying right once if such messages are still being delivered with 2048-bit RSA encryption or a comparable encryption method.